So I've been given a lot of problems. First thing is that I've given less of time, you're waiting for tea, and I've got to keep you all occupied. The other thing is that I'm the only person speaking about observational astronomy today. You're all theory, all will hear theory after me, theory before me. So I have an important task to get you convinced that everybody must observe, right? Because after all, we know that the universe is beautiful, right? If it's beautiful, we should look at it. Instead of looking at pen and paper and writing things, look at it. So how do we look at it? Now this is, I wanted to, since there's a lot of young crowd around, I wanted to get your attention to something very important going on in the country. After Mangalyaan, another important thing that the country is involved with is the 30-meter telescope. Okay, so I'll tell you the story about the 30-meter telescope and the Indian contribution and the Indian role in that. And I'm a member of one of the ISDTs, so I promote my ISDT a little bit more, and we'll talk about what are the kind of things we do. Yeah. That's a painting on fate is in our eyes, right? For what astronomy is a science in which your observations or your detector is what actually defines what you're going to do, right? When you look at your eye, you're crippled with your eye, or that's all you can see. The eye is a very good detector, you can see very well. And you do that with a telescope. Now a telescope was actually discovered by chance in a lens maker's shop, literally by children who actually noticed where you could actually use a convex. The application was found in defense, where you could look. In 1609, when Galileo actually pointed the telescope at the sky to actually look at stars. Before that, we don't have any. Galileo actually paid a good price for this also, because we'll see why he was. Yeah. You see that the church was not too happy with what Galileo had to say with this thing. Why, you see? The other way around. Okay, sorry. So you can see here Galileo looking at the stars and the church not too happy with what he did, and you'll see why. You see that just a simple act of just using a small telescope. The telescope he used was a very small telescope, but with that he could actually see the satellites of Jupiter. Jupiter, which you can see out in the sky just now, also has a whole lot of satellites, of which 4 of them are very easily observable, even with the telescope which Galileo did. Right? So immediately he questioned the then prevalent geocentric theory, where everybody thought that the Earth was the center and everything else went around it. Here he already could show you an example that look, you have these guys not going around the Earth. You have this bunch of people not doing that. So for you to assume that everything goes around the Earth is not true, right? He also could actually see the phases of Venus. Venus, you often see it in the sky, and it's interesting to see that if you see it with a telescope, you'll see the Venus showing phases. Actually phases like the moon. You can see crescent Venus, you'll see half Venus, you'll see full Venus. And this typically happens only for planets which are inside the Earth's orbit. So it would have happened with Mercury and Venus. It doesn't happen with the planets which are outside the Earth's orbit, right? But Mercury is too close to the Sun, so we don't see the face of Mercury ever. But you can see the faces of Venus. And the only way of explaining the face of Venus was with heliocentric theory, saying that the orbit of Venus was inside the orbit of the Earth, right? He also saw the craters of the moon, and he could actually resolve the stars of the Milky Way. So what happened is that this actually got a very different, the worldview at that time was something like this, okay, which is a very primitive worldview where you have the Earth in the center, you have everyone going around the Earth, right? And immediately what he observed, the little bit that he could observe, was enough to question the present worldview, right? And that's how even Stephen Hawking referred to that as the birth of modern science, where you're actually observing things which contradict with what you actually think things are. And that's when you're forced to change the way you think, because you can see it is not what you think, right? So even Einstein called him the father of modern science, and that's the very base of science. You have to observe, because only if you observe do you try to explain using a theory. And when you make a theory, you improve on your theory with what you observe. So there is a constant give and take between theory and observations. There's no harm in doing theory, you have to do theory, but you have to observe, explain it with your theory, improvise your theory using further observations. And that is the very process of science. When you do an experiment, you observe it, you explain it with your theory. And these two things have to go side by side so that you're actually explaining the real world, right? You're actually explaining concrete things. Next please. So that's the importance of the telescope. So I said even a small telescope had a very big role to play for it. Galileo was in house arrest and he went through a lot of problems for looking through that telescope. We don't go through that kind. So what is the job of a telescope? A telescope basically is, photons are raining down from stars, galaxies, whatever. You have to collect them. So your light gathering area depends upon the diameter of your mirror, right? So first job the telescope does is it gives you a light gathering power, which goes as d squared because it is the area, it's proportional to the area, pi r squared or pi d squared. The other important job of the telescope is resolving power. Now we all know that there's something called diffraction, right? Light is not a particle, it's a wave, and therefore it shows diffraction effects. And therefore for every point source of light you get a diffraction pattern, right? And if your 2 point sources are very close together, they smudge, they spoil you don't see it too well, you see blurred images, and you cannot resolve or you cannot see detail onto that image. So here is an example of an unresolved thing, and the same thing if I were to resolve it, I can actually see details. So that is what the telescope does, right? It actually lets you see detail on what you're seeing. Like when I said craters on the moon or the faces of Venus, you cannot see that with your naked eye, but you see it with the telescope. Magnification is also an important aspect, but it's not what the telescope is meant for. Right? Magnification is not at all not the important factor. What is important are these two factors. And how faint you actually see depends upon obviously this D factor. Your D factor will increase your light gathering power, how faint you can see. And it also, the resolving power, this is the first, n equal to 1 Aries disk, which you get at diffraction, which is given by 1.22 lambda by D. So here you can see your resolving power improves with a larger diameter, okay, because this should be a smaller number, and your light gathering power goes as the D squared. Okay, so obviously a big telescope means more fainter and better resolved. Now just increasing the size of your telescope is not enough, okay. Just by getting a big telescope you don't, because we have another big problem is that we are covered by atmosphere, and atmosphere has turbulence, right? And because of that there is a movement of light. For example, when you look at the star, you see the star twinkling, right? What is actually happening when the star twinkles? Because the air mass between you and the star, there's a variation in the density and there's a fluctuation. Hence the position of the star slightly keeps shifting, right? So when you're seeing, since everybody is using that, so your star, which you actually, when you looked at your star over here, if you were actually looking as a particle thing, your bullet says it's here. But because it's getting slightly shifted because of turbulence, this thing moves over here. And that's what we call twinkling, correct? In the case of a planet, we don't see this twinkling effect because the planet has a larger size. And so when that displacement takes place, the displacement is so small that we don't notice the change. So for example, the moon or any planet which has a larger size, we don't see this effect. We see it only with stars, right? But you see that this twinkle is actually an aberration. It's a problem, right? So what we actually want to do is remove the twinkle from the star. We don't want it to twinkle because the twinkling is giving us wrong information, right? And for using that, there is something called adaptive optics, which is also a very important necessity in a big telescope to have adaptive optics, because what it basically does is it corrects for the atmosphere. Okay? So for example, if I have light from the telescope coming in, this wavefront, which should have been a parallel wavefront, is actually distorted, right, because of the atmosphere. So when I collect it, I actually use this thing to use a control system to correct my distortions, and so that here I can get a nice parallel beam. And using this parallel beam, I actually look at it. So this is a simple schema you can see, but what is done in observatories is either you have a good star, but often you don't have a good star, right? And therefore you can actually use a laser beam to actually create an artificial star, You take a laser beam, create an artificial star up there, and then you use that. You know your laser beam has what, a parallel wavefront or whatever wavefront. Use that to correct it and get your corrected image. So you can look at this with the same telescope. If you have adaptive optics, if you don't have adaptive optics, you'll see this. See, this is similar to twinkling. What is happening is light from some point of view is getting mixed up over here. So you are seeing a kind of smudged image. But if I use adaptive optics on the same telescope, I can actually fix my points over here. So I stop that twinkling and I get my thing over here using the same telescope. You have not changed your telescope. You have just corrected with adaptive optics. So all telescopes, even the Hubble Space Telescope or all these telescopes, necessarily have to have adaptive optics, because otherwise the advantage you are getting from a bigger diameter is lost, because you are further smudging your image. You are not improving. Even though you increased your D. We said with D, if you increase D, you improve your resolving power, but you lose on it because of the atmosphere. So like I said, one solution is you send the telescope out into space, like the Hubble Space Telescope, or you do something like this, or what we do is often we do both. In Hubble Space Telescope, they've actually done both, because you are sending it up, but it's not that you're devoid of atmosphere. You still have some disturbance. So you send it out, so you minimize the atmosphere effects. Plus you have adaptive optics, and you'll see even on the net you can see images of Hubble Space Telescope with and without adaptive optics, and you can see the advantage you get. Next. Another problem is if you want to make a big telescope, making a big mirror is very, very difficult. Yeah? People have tried it out, and the maximum size people have managed is 8 meters in diameter. 8 meters is about the size of this room. Yeah? Think of a mirror which has an 8 meter diameter, about the size of this room, a single piece. Right? That has still been done in the telescope which is called the Large Binocular Telescope. This actually has 2 mirrors which are 8.4 meters, single pieces. Right? But otherwise, if you want to make bigger than that, you can't make more than 8 meters, because it's very, very difficult. There are lots of problems in having this big mirror, because it has to be polished correctly, silvered correctly, all those aspects are there. So what is done is you actually use what are called segmented mirrors. You have pieces which you are actually doing. So all big telescopes, 10 meter types, are all segmented mirrors. Yeah. Next please. So I've written a list of segmented mirrors which is already very large, and these are already, all these are this is not yet operational, but all these telescopes are operational telescopes with segmented mirrors. So for example, you see the Keck telescopes. The Keck telescopes are amongst the best telescopes. These are 10 meter, 2 telescopes. 2 telescopes of 10 meter class, and they are made of segments. You have this Hobble-Everly telescope with 9.2 meters, you have 91. It's not like a hexagon, like a honeycomb structure. There is an image of it. There's the SALT. This is the South African Large Telescope, again 10 meter, 91 hexagon. You have the Grand Telescope in Karen Islands. This is also 36. And you have a lot of such telescopes. The new Space Telescope, which is going to go out soon, which is called the James Webb Space Telescope. The Hubble Space is a single mirror, 2.5 meters. Okay? James Webb Space Telescope is an 18 meter segment, which is going to be almost 6 meters in size. So you have a 6 meter telescope in space soon. 2018 is the present date. So those are the already operational segmented telescopes. So let's make bigger, let's make more. So at present, what is on the pipeline is that the Europeans are making what is called the Extremely Large Telescope, EELT, which will have a 39.3 meter diameter. Okay? This is a segmented telescope, obviously. There's the 30 meter telescope which I'm going to talk about today. 30 meters is really huge. Right? It's bigger than any of the classrooms you sit in. There is the GMT, which is also, you have 8 meters and various others. I'm not going to talk about all these. Next please. So the future is bright, and the best sample which is used for construction of such a telescope is the Keck telescope. This is a set of optical telescopes, 2 telescopes, 10 meters each. Each of them have a 10 meter diameter, and they are actually used to do what is called optical interferometry. Okay? In radio, interferometry is a very established, well-established technique, but it is now also being used in optical, and it takes a lot of electronics and a lot of other things to actually do interferometry in optical wavelengths. Right? This is the telescope. We'll start with so Mauna Kea was the site at which the 30 meter telescope was planned. Okay? This is an island in Hawaii. which has excellent seeing conditions. Seeing is when you don't have a turbulent atmosphere, you can look well. And you can see that there are a whole lot of very well-known telescopes which are all there on this peak over here. And the 30-meter telescope is also going to be coming up in Hawaii. Next, please. So this is what is happening in the world, right? We are talking about existing 10-meter telescopes, and we are talking about people building 30 meters, 40 meters. That's the kind of numbers we are talking about, right? Globally. Now, what is the scene in India? What are the kind of telescopes we have in India? We have the Japa Gangapur Observatory, which is not too far from here, 60 kilometers from here. This is a 1.2 meter telescope. This was made in 1960s. Okay. Then we have telescope at Nainital, which is again a 1.2 meter. But the Nainital people are coming up very, very soon. In 1 or 2 months, we'll have almost it's a 3.6 meter telescope, which is coming up at a place called Devasthal. Okay, so that's a 3.6 meter telescope optical. This is the Ayuka Observatory, IGO. This is Ayuka Observatory. This is again 2 meter telescope, which came up in 2006. Then you have the Indian Astronomical Observatory. This is in Ladakh, in Leh. This is a 2 meter telescope in Ladakh. This one is the telescope which is in Rajasthan, in Mount Abu, which is the Mount Abu Infrared Observatory. Yeah, this is the Nainital one. So this is the kind of scene we have. This thing has come out very badly, so I'll skip this, but this is just a comparison of the sizes of the different telescopes available at present, and this is the TMT. So I'll skip this because it's not good. Yeah. So the question is, if the whole world is looking at something like that, agreed, we have limited resources. With our resources, we have to build. But it's not that only we are the ones who have limited resources, right? The TMT itself, when it was proposed by Caltech, universities in California, there's Canada, Japan, China, India. It was realized that this kind of a telescope costs about $1.5 billion. Okay, that's the cost of this telescope. The ELT is going to cost 1.5 billion euro. So that's the kind of money that you need to build this telescope. But we want to build it. So what do? So what you do is you collect a whole lot of people to contribute into that, right? And you look at this telescope. It's like a dream telescope. You have 30 meters is the diameter of the telescope. You have 492 segments which make up the segmented mirror. Okay? Each piece is 1.45 meters in diameter. Each piece. Okay? It will range from ultraviolet to infrared. Adaptive optics, each thing it has a 20 arc field of view, you have higher retinal resolution, sensitivity, etc. So what was realized is that the best thing is people get together and build it together, right? So next, movie time. Okay, so I first of all want to convince you what's so great about it. So you will see some movie, 2 movies. I'll show you. No, first flyby. So first you're going to see a very fast 50-second flyby of the telescope. This is obviously an artist's impression. There's no telescope at present. We just have the summit. The construction has started. So you can look at this. This is the telescope mirror over here, and you have this dome which has been designed very differently. Most telescopes you never see a dome like this. It has a very different kind of dome because it has to accommodate the mirror. You see the segments are over here. So if you look at it, it looks like a single piece. You don't even notice that it's made up of 492 pieces. But you have this whole massive structure which is some 2,000 tons, which is supported by a mesh kind of thing which supports it, and you have this grand thing which is over here, this one. There was one which actually had the maybe in the optical part it's there. It actually had a comparison. Those windows which you saw in it would actually be a man's height. So this thing would be like a football stadium, the size of this. Okay. Here you have an image of the optical path. You have light coming in. This is the primary mirror. It hits the secondary mirror. Secondary mirror over here, and then the secondary mirror itself is a 4 meters mirror. Okay, which is larger than any of the telescopes we have. And sorry. Then there's a third mirror. There's an M3. There are 3 mirrors. And here on the side you have all these. These are all the instruments. Okay. So you have these back-end instruments which are kept over here, which will actually detect the light and do spectroscopy or imaging or whatever they are supposed to be doing, are being done by that. So movie time is over. We'll go back to that. Okay. it was a green kind of a project. Obviously, India wanted to get into it because it was realized that we need to have better telescopes because, like I said, this is technology driven. If you have a 4-meter telescope and the whole world is using a 30-meter telescope, obviously there's going to be a big difference between the kind of results and the observations you will get compared to there, right? So you have to be into the race properly. You can't be expecting that your 4-meter telescopes are going to give you results which are going to compare with what people are going to do with bigger ones. So India got into this thing. And part of the effect was because of Mangalyaan. The next day itself it was signed. Before that already there was a green signal on getting into it, but finally the deal was then signed by Department of Science and Technology, where actually India could formally contribute for the TMT. So we paid something like 1,300 crores onto the TMT. The good thing about the TMT is that India is participating 70% in kind, 30% in cash. Okay? Which is a very good thing because one big deal in this is that India was not too good in instrumentation. Okay? Most of the time people would buy ready-made telescopes, use them and handle it like that. But now in India people are developing instrumentation groups where actually they are building instruments for their telescopes themselves. And India has taken up the job of, see, each segmented mirror has to, these are the things we are going to contribute in 70%, and this is all going to be done by Indian companies. So finally, though the funding is going for TMT, but you are going to be paying Indian companies to do these jobs for you. So the 70% cash actually bounces back to the country. It doesn't go outside, right? So 70% bounces back, you are using it for your own industry, for high technology things. And if you do a good job of it, probably the country would be then beginning to lead in telescope building or certain aspects of them, which they can then use for other countries where they would order it from them. Right? Because there are not too many people in the world who have expertise in making things like this. So if you see in each segmented mirror, you have actually 12 edge centers, totally 3,234 centers. For M1 is the primary mirror. So we've already produced some 25 prototype centers. These have already been approved also. And this is being done by a company which is in Puducherry. Okay? They are actually developing these things. Accentuators, all the hexagonal adaptive optics is actually changing the mirror positions, adjusting it and all that, using these edge sensors and the accentuators. And you need totally 1,476 accentuators. These are also being built by a company which is in Bangalore. So you have some 10 such prototype ones. So what has to be done is the country makes it, you send it there for approval. When they say, okay, your quality is met certain quality standards and all that, then you can do the rest. So India is making the accentuators. We are also making what is called the segment support assemblies. Each mirror segment, there are some support assemblies for the mirror. You have to support the segments and all that. That's also being done by Indian companies. I think Godrej is doing this. And we're doing another important job, which will be polishing of the segments. There are 492 segments, not all. We're going to be doing part of them. So we got to polish it. This is using very specialized techniques. There's a technique called stress mirror polishing technique or CNC approach. We're doing that. And then we should also, obviously, we're doing something that India has always been good at, software. So all the software for TMT is being developed by Indians. That is the observatory software with which you're observing, the data management system, and image and object catalogs. All these are being developed in India for the TMT. There are a lot of other minor projects also, event services, infrared guide star catalogs. So what is being done is it's being converted into a win-win situation. You want something, you tell me, pay me for it. I say, okay, I pay you, but I end up paying myself only. So what is being done is I am using it to build up an expertise in the country in building such things which are not trivial things technologically, right? They are challenging things technologically. So the country is learning, developing a certain expertise, and at the same time the 70% is coming back. That was one of the major reasons why India opted for the TMT. Otherwise, there was an option of either applying for ELT, the European one, or even the GMT, which is the Magellan telescope, giant Magellan. But TMT, it could be worked out with this 70-30 breakup. 30 anyway they need for maintenance and other construction, other things. So that could not be reduced. But this is one of the reasons why we went in for TMT. So in principle, though like I told you 1,300 crores is what we are putting in, a good amount of it is coming back to us. 70% is going to be ours. Right? Now, my role is not in making all those things. there are what are called these international science-driven teams. One job is constructing the telescope and the instruments, right? How are they constructed? There are different teams, different countries who are participating in the construction. Parallelly, while it's being constructed, you also need what are called, these are called international science-driven teams, which are teams which are actually looking at the science that can be done with the telescope. Because it shouldn't be that tomorrow you have the telescope and you don't know what to do with it, right? Then you should have thought of, I'm going to get the telescope and I'm going to use it for X, Y, Z, whatever purpose you're going to be using for. So these are the whole, the ISDTs, the teams. I am part of this team, which is on formation of stars and planets, okay? But otherwise you have different things, because like a telescope like this can be used for various purposes. You could even use it for fundamental physics and cosmology, looking for black holes, looking for looking at the early universe, galaxy formation, intergalactic medium. You could look for supermassive black holes using this thing. You could actually look at Milky Way and nearby galaxies. There's a lot to see even in Milky Way and nearby galaxies also. And the formation of stars and planets to actually look at, see, no telescopes in this day. Let's see, look at a star in magnification, excluding the sun. Excluding the sun, you cannot zoom and look at any star. So you're actually not looking at a star from close. You're not seeing it. But with this one, you can actually look at stars and close when they are being formed. You can actually look at exoplanets. Right? If you have some potential, there's already something called Kepler, which is a satellite looking for exoplanets. So if you have a Kepler list, these are the potential candidates. You can actually zoom in and look at your potential candidates using this big telescope, right? And various things in the solar system. There's also something very interesting in science called the time domain science, looking for transits, for variability. Because variability could be because of the star of the galaxy. It could be even a black hole, some lensing effect. It could be transits, it could be exoplanets, various things which can show up as time domain science. So there are these various ISDTs. Now I'll do a little bit on my ISDT, which is the one on birth of stars and planetary systems. So obviously it is to look at the birth and early evolution of stars. Because we all know by now that planets are actually a byproduct of star formation, right? And we are byproducts of that planet formation, right? So if you want to ask yourself the question about your origin, you better go back to the origin of the sun. Because with the sun was formed, you had the earth forming as a byproduct, and we were just byproducts of that byproduct, right? So you need to immediately start with that, right? So you can look for potential origins of life. So therefore, like I said, star formation is very interesting to, this is basically, throughout the universe, you see gravity does the job. Gravity does the job of basically converting diffuse gas into stars, black holes, galaxies, whatever it is. And star formation actually bridges this gap between planetary and galaxy evolution. So you have it at different scales. It could even start off with the different scales at which you are actually moving from diffuse gas to stars and planets. Next, please. So I'll just skip through this very fast. Basically what happens is this telescope is going to be from ultraviolet to infrared. Infrared, if you have locations in the sky where you have a lot of gas and dust, you cannot see it in optic, you will see it in infrared. And that's what this telescope is. This is a BLT image which you can actually see regions of the sky which are, it's a dark molecular cloud which is actually dark. You cannot see in optical, but you see it in infrared. Yeah, next. So you can actually study star formation, see the efficiency of star formation. Like said, most stars form in groups, so you can actually study the groups that you have. These are various star cluster groups. And again, you have this thing. You can actually look at star clusters not only in our galaxy, this is in the Orion Nebula, but this one is, this is also in the galaxy only, but you can look at various star clusters within the galaxy, outside the galaxy, compare them, because you will have that kind of resolution. If you did not have resolution, then you couldn't have seen it, right? And you can actually see what is called the mass function, which is telling you how is the mass distributed from a cloud which actually forms stars. Next, please. And the feedback. There's a lot about this stuff. How actually stars form, accretion disks. When stars form, there's an accretion disk around it. And even with the Hubble Space Telescope, you can actually look at accretion disks around stars. In this case, we will see it even better. You can actually look at cores and see the regions where stars are forming and compare the core mass function with what is called the initial mass function. And so let's picture this. 2022 is actually the time when the TMP should be ready, 7 years from now. And By then, you already have VLT, Spitzer. Spitzer is another space telescope I hope you are aware of. WISE is also there. There's Herschel, also a space telescope. All these would be here already for a decade. Okay, and you will have a lot of astro data available from all these very good telescopes, and it would actually cover the whole electromagnetic spectrum. So you can actually move from this end to that end with a lot of data. India has not only done this with TMT, just for a footnote, there's also something what is called the square kilometer array, which is also a very big project, which is a project for radio telescopes. And again, in this case also what India is a participant, but India is an associate member for the SKA, the square kilometer array, which is a similar huge project in the radio side. We have not yet become proper full members, we are associate members. Hope is there that we become full members, because that's the only way. You contribute in some way, then you'd actually be part of the instrumentation building process, plus once the telescope is ready, you get a certain amount of telescope time, which your community can use, right? Because you get the amount of time you get on the telescope is a fraction of the amount of money you've put into, or whatever your contributing part is. Right? We've also contributed to SALT also. So by 2022, you'll already have this, the James Webb Space Telescope. This would also be out, and this is the kind of precision we'll actually be able to see. This is the European one. It would not just be this telescope, it's going to be data from many more telescopes which will be available, which can be used to understand the universe better. And these are some of the first light instruments which are going to be there in the TMT. It's the IRIS. Please, there's also the IRMS. There are three first light instruments, there's MOBI, IRIS and IRMS. These are the first three instruments which will be there on the telescope, when the telescope is set. And just conclude with this, that the excitement of the next generation of astronomical facilities is not in the old questions which shall be answered, but in the new questions that they will raise. Yeah? At present we were just referring to what are the old questions, but there are definitely going to be some new questions which will come up with this, which all of you will be there to solve.